Hello class, this is lesson 3-3 about linearity and continuity of graphs. So we're going to look at three different graphs here. The first type is called a discrete graph, and this is a graph that is made up of unconnected points. So let me go ahead and just show you a random example. Literally on your graph, you would just see some different points, and that's it. They're not connected in any way. There's just some points. The next type is called a continuous graph, and this is a graph that is made up of connected lines or curves. So similar to last time, I can just make up some random example where I have this curvy, straight looking line that just keeps on going, and that is called a continuous graph. Now, it's possible that you have a graph that is neither discrete nor continuous, and this is where some points you'll find are connected by lines or curves, but it's not that way everywhere on your graph, okay? So, for instance, I'll just draw another random example for you. I'll have a few points on here, and they can be connected by either a segment or a ray going in one direction. So let's look at a few examples now, and let's determine if they're discrete, continuous, or neither. So for my first example, I would say neither, because it is not made up of a collection of only points or one continuous line or curve. And if I was going to describe the domain, which is the x values, or the range, which is the y values, it's kind of hard to specify because I have some points and then I have some intervals. So I think that I would just say that it is different intervals of values, okay? And that's how we would just describe it for this one scenario. For our next example, I would say that this is a discrete graph because it is made up of very specific points that are not connected anywhere. So if I was going to list the domain or list the range, we've done this before. The domain would just be listing out the x values of all the points. The range would be listing out all of the y values of all the points. So I could just say that it was going to be based on the set of individual values, and typically I would write it out. I'm just not going to do it right now. My last graph is a continuous graph, and I think that's pretty clear to see. If I'm going to describe the domain or the x values, I could say that it is all real numbers. I can see that. But for the range, to describe the y values, there is a limit on it. There's an interval. And I can see it's starting at -3 and then it's going above -3. So it's all the y values that are greater than -3. So now I have 4 real-life examples to see if they are continuous or discrete. So the first says the altitude of an airplane over time. So if you were given this scenario and you were going to draw an airplane going high in the sky and how high up it's going, it would go up from the ground and then it would stay and then it would eventually come back down, right, as it's landing. So this would be continuous because at any point, at any second in time, I can find its altitude. Next is the cost of concert tickets. So I would have the price of 1 ticket and 2 tickets and 3 tickets and 4 tickets and so on, right? So this is going to be discrete because I don't know the price of 1.5 tickets, if that makes sense. Next is the number of students in each grade. So maybe kindergarten has a number up there. First grade is really high, second grade is really low, third and fourth grade are kind of similar. So this would also be discrete because I don't know how many students are in second and a half grade, if that makes sense. The last one is temperature throughout the day. So if you're going to graph this, it would be starting at a certain temp and going up high and then coming back down at nighttime. So this again would be continuous because at any point in time, I can find the temperature. So now let's move on to what we call a linear function, okay? So this is a function whose graph is a straight line. And we can write the equation of this function and the equation is going to be written in what we call standard form. So it's a specific order, a times x plus some other number b times y is equal to some other number c. Okay, so if I can put it in that form, it is called a linear function. So now let's discuss a nonlinear function. And this is a function that, even though there might be an equation that follows the graph of it, it is a function whose graph does not contain points that are all on one straight line. So a lot of times the line might be curved. And so let's look at some examples. Is y equal to 4x squared minus, in parentheses, 2x squared plus 3x minus 5 a linear function? So let's simplify this as much as we can. 2x times 2x is 4x squared. And then looking, 4x squared minus 4x squared is 0. So simplify, this is y is equal to 3x minus 5. I'm going to see if I can get this into standard form. So I'm going to move the 3x to the left-hand side. And when I do that, I have negative 3x plus y is equal to negative 5. And since this is in standard form, this is a linear function. If I was going to graph it, it would be one straight line. In my next example, I have 4x minus, in parentheses, 2y squared equal to 3, which is the same as 4y squared. And that's as simple as it can get. And since I still have that y squared instead of just a y, this would be a non-linear function. This would probably give me a curved line. My next example, I have y is equal to 3x cubed minus x cubed plus 3x plus 6. 3x cubed minus x cubed, it leaves me with 2x cubed. And that's as simple as I can get it. So because I have the x cubed still in my equation, this is also going to be a non-linear function. So again, the graph of this would probably be some type of curved graph. All right, my final example is 3x squared minus the square root of 9 times x squared minus y is equal to 17. So I know that I can take the square root of 9, which is 3, so that's 3x squared minus y equal to 17. And 3x squared minus 3x squared cancels each other out, so I am left with negative y is equal to 17. Now, if you notice, I don't have an x here, but if the number in front of it was a 0, then this would be in standard form, which means that this is a linear function. Okay? All right, to conclude, I have two more examples, and this time we're going to look at a table of different values to see if they model a linear function. So for instance, I can see that negative 5 times 3 is equal to negative 15. And also negative 1 times 3 is negative 3. 0 times 3 is 0. 2 times 3 is 6. 3 times 3 is 9. And 7 times 3 is 21. So I found a pattern. Every time I'm multiplying 3 times the value of x, and that equals the y value. And now I'm going to subtract 3x on both sides to rewrite my equation. So negative 3x plus y is equal to 0, which is in standard form, which means that this is a linear function. Okay? So now I have one more table here. I could graph these values to see if they line up on a straight line, but I want to see if I can find a pattern as well, just like my last example. And I'm not finding anything that's just standing out right away, but I do know that 2 cubed is 8. And if I multiply that by negative 1, that gives me negative 8. So also 3 cubed is 27. Likewise, if I multiply it by negative 1, that gives me negative 27. And I can see this pattern repeating in just about all my rows. 7 cubed is 343. I can multiply that by negative 1. So the pattern here, y is equal to -1 times that x value cubed. But that already is not going to give me a standard form equation, which means that this is going to be a nonlinear function. And that's it. So I hope that this lesson made sense on continuous, discrete, linear, nonlinear functions. But please let me know if you have any questions when you come into class.